Hi everyone, my name is Karl Wust. I'm a security researcher from ETH Zurich, and the work that I present here is joint work with Peter Tankov, Sasha Lominovic, and Mohamed Rabidashti. So usually when we open a file, if we open an image file for example, we expect something like this. The file viewer pops up and shows us the image that we want to see. In this case, a nice photo of Zurich. But sometimes files get corrupted for different reasons, transmission errors, degraded storage, or some other reasons. And in some cases, we can still open the image, but it will look something like this. So we get some artifacts here. In this case, we have some part of the image that is on the bottom right that should actually be on the bottom left. But we can still open the image and we can still see that this is a picture of Zurich. And if we compare this picture to the previous one, we can still clearly see that this is originally the same image. So we can still get some information out of this. But we can have different kinds of corruptions. And these corruptions lead to something like this. So the file viewer pops up and tells us could not load image Zurich.png because this image is not a PNG file. And in this case, the file header of the PNG is broken. That's why the image viewer doesn't recognize it as a PNG file, and it produces an error, and we don't get anything. And these are the kinds of corruptions that we're concerned with and that we worked on. So what I'll present to you in this talk is about repairing these kinds of files, so files that cannot be opened by a file viewer. So this means that ideally we get from producing an error to at some point opening the file. However, if we're only able to open the file with some artifacts showing, we can still get some information out of this, so we're still somewhat happy. So our goals are that we have an invalid input, a file that we cannot open, and we want to get file viewer at some point at a later time to produce an output that is visually, for pictures, visually as similar as possible to the original file. For other files, the similarity depends on whatever we have. For example, if we have a PDF, a text-based PDF, we might want the text to be as close to the original as possible. And our approach differs a bit from previous approaches in that we don't actually change the data of the file, but instead we modify the execution of the file viewer when we want to open a corrupted file. And we learn the behavior that we want to enforce by opening a lot of valid files and see how the file viewer behaves when opening these valid files. And so our tool works in two phases basically. We first have the training phase in which we learn the behavior, and then we have the force open phase in which we force the file viewer to actually open the corrupted file. And in a file viewer execution, we usually have some checks in there. So in this case, this is an example for a PNG file viewer. We have a check that says, does the file start with the bytes 137, 80, 78, and so on. This is the PNG file signature, so this is one of the first checks that is done to see whether this is a valid PNG file. And if this check, if this condition is false, then we get this pop-up with the error telling us it couldn't open the file. If this check succeeds, then we continue the execution. And then at a later point in time, we might have another check that checks whether the CRC checksum that is stored in the file is actually equal to the CRC checksum that we compute from the data of the file. And there again, if this check succeeds, we continue the execution, otherwise we'll produce an error, this time telling us that the CRC check failed. And now, the behavior that we do want is basically this path down here. What we don't want is the program producing these errors, right? Because at the end we just open the file. So if we land here, because this condition is false, and we don't reach our goal, the program doesn't open the file. The same for this here. So what we can do is just force the program to continue down the path of, down the left path in this case, and force the checks to always evaluate to true. And this way we won't get these errors. So if we look at the bigger picture here, we get some execution tree. So each of these bubbles here is a conditional. And so we have one valid file here that for the first conditional takes the left branch, and for the next conditional that is on the path, it takes the right branch, and so on, until at the bottom here, the file viewer opens the file. And for example, if you're for a PNG, it would display the image here. And for a different file, if you have an invalid file that we get as input, and we might take a different path. So let's say at the first conditional, we continue on the right path, and then we have another check, and there we again continue to the right path, and then here the image viewer will display an error message, and the file will not open. And so the valid files are files that satisfy the file format specification, and the invalid files do not satisfy the file format specification. And this format specification can actually be implicit in the program, so this doesn't need to be a specification that is written down somewhere and standardized by some organization, but this can be an implicit specification regarding the actual file viewer that we look at, and the constraints that are given by this format specification manifest in the execution of the program through these conditional statements that we have here and through these checks. So what we can do, we can record the branches that are taken when we execute the file viewer with a valid file as an input. So in this case, we have the file from before, where we have this execution path here. We can have an additional file where the execution always takes the left branches, and we can record multiple such branches, such paths, and we get this collection of branches that are taken. And we see here that for the first check, for example, some valid files take the left branch and some valid files take the right branch. So there we don't get any information about whether this file is valid or not. But if you look at this check here on the right, we see that all of the valid files actually take the left branch. So if we are at this conditional here, then we know that if we want to open a file, we have to take the left branch, otherwise we will get an error at some point. So we can actually basically throw away all of the recorded branches where some files take the left branch and some files take the right branch, and just keep the ones for the conditionals where the file viewer behaves the same way with all valid files as inputs. And so we're left with some smaller collection of branches, and we know that these branches are always taken if a valid file is an input and we reach this conditional. So now if we go back to the execution path of the invalid file that we had before, we actually, at first check, we don't have any information yet about the validity of the file, because some valid files take the left branch and some take the right branch. So we just continue the execution to this check here. But at this point, we actually know that all of the valid files take the left branch. So instead of going the right path and being 100% sure that we will reach an error at some point, we can just force the program to take the left branch instead. And we will continue the execution and go to this next check. At this point, we again know that all of the valid files take the right path, so we will again enforce this path and reach this check. And here, we actually, again, don't know which way the file should go if we want to open it. So the check is up to the file viewer, and in this example, let's say it takes the left branch, and then hopefully we will be able to see the file here. So hopefully the file viewer will open the file when we reach this point. This approach, the nice thing about this is that we can implement this as a black box approach, meaning that we don't need any information about the file format. We don't need access to a source code. All we need is a binary of the file viewer and some valid files that we can train with. And we use binary instrumentation execution hijacking, so we, when recording the program executions for valid files, we inject function after each jump statement that records from which location the jump goes to which destination. And then after we collect all of these traces for the different program executions, we can combine them and then again use instrumentation to hijack the execution of the file viewer when we want to open a corrupted file, and insert unconditional jumps before the jumps that we want to force, so the program will always take the same path at these conditions. And this makes the approach generic, because we don't need any format-specific heuristics. We inherently don't have any format-specific heuristics, but instead we learn how the file viewer should behave in order to open these broken files. We implemented this in Python and C++, so with C++ we use the Intel PIN framework for instrumentation, and then we have a wrapper around that in Python that does the merging of the different traces and gives us the branches that we actually want to force. And for the evaluation, we used random file corruptions. So for this, we actually, let's say if we want to corrupt one single byte, then we corrupt a byte in the file, try to open it with the file viewer. If it succeeds, then we throw this file away and try again with a new byte that we corrupt, and do this until we get a file that cannot be opened. So we get files that are invalid, and we get a uniform distribution on the corrupted files of this type. Now to the results. So we compared our results to two reference tools for, and we evaluated this for PNG files, JPEG files, and PDF files. And for the image files, we compared it to Pix Recovery, which is a commercial image recovery tool, image repair tool. And for PDFs, we compared it to PDFDK, which is a PDF editing toolkit that is also able to repair corrupted files. And our approach, or the one thing that is very surprising, is that the overlap of the files that our tool is able to repair and that the reference tools are able to repair is quite small. So we see here for PDF and for PDFs, actually only less than 1% of all files were repaired by both tools, but a significant amount was repaired by either of the tools. So our approach actually increases the total success rate if it's used in combination with existing tools. And for PNG files, our approach is actually more successful than the reference tool. And again, the total success rate is increased significantly. The same goes for JPEG files. So for PNG files, the overall success rate is increased by roughly 85%. For JPEGs, about 35%, and for PDFs, about 30%. Yeah, then this is some more detailed results for PNGs. So PNG has very nicely structured file format, which makes it nice to sort of analyze. And these are files with 1 byte corruptions, so we exactly know in which part of the file the corruptions are. And we see with this that some corruptions are easier to repair than others, which makes sense, because if we have a file header that basically always looks the same, we should be able to repair more of these files than for some other corruptions. And we actually see that a lot of these files we can repair. On the other hand, if we look at this line here, so iHeader is the image header of the PNG, and this stores information such, for example, the image dimensions. And these corruptions that we have here, chunk data, other, most of these are actually in the image dimensions. So we see that for these kinds of corruptions, we're only able to repair very, very few files. So this file here that we could repair is actually not in the image dimensions. I think for the image dimensions, we weren't able to repair any of them, because this is very highly data dependent, and there's no simple if then else statement where you could force the direction of the branch. So this is one type of corruption that we cannot handle well. But for stuff like CRC checks, the approach works reasonably well. For things that are similar or the same in all images, the approach works quite well. And also for these ancillary chunks, these are chunks that are not required by the PNG standard. So these are additional chunks that are not necessary they don't have to be present in a PNG for it to be valid. And in these, we're also quite good in repairing them, because they can sort of be ignored. Okay, so some of the limitations. As I already mentioned, the approach is not suitable for highly data-dependent corruptions. And also, it requires if-then-else statements for the conditions that it works with. So if we have some jump table where it jumps to some location that is dependent on some data, this will not work because we don't have a simple branch, right? And one of the most important things is that using this, you can get unwanted side effects, and it should be sandboxed in an adversarial environment, because if the program if you force the program to behave as if all input files are valid, then we also don't do any checks anymore for buffer overflows, for example. So this will very likely make the program vulnerable, and thus it should be sandboxed if you expect an adversary to be present. Alright, so we're already at the conclusion. The approach I presented is lightweight, and it's a black box approach that modifies the execution of the file viewer instead of modifying the file itself. We applied the approach to PNG, JPEG, and PDF files, but it is applicable to any file format. And it works very well complementary to existing tools and is able to increase the overall success rate significantly. And if you want to look at the tools, they're available online for you to download if you wish. All right, I'm open to questions now.
Yeah, so we've got a few minutes for questions.
I have a question to the execution tree that you showed.
Yeah.
And you have the first switch that you have there. You said it's not important, or you don't look at you don't modify the decision because on both sides you have valid files.
Yes.
So what I was thinking when I was looking at this in a hypothetical decoder, this might be, the first check might be something like, which file version do I have? Which version of the file format that I'm using I might have? So if the error in the file is directly in that small part, so it's not like saying it's version 1 of the file format, but version 2.
Yeah.
Then that might be the only modification that stops this file from being correctly interpreted. And by just accepting that decision, you might go directly along the path that leads to a non-valid file, but if you would change exactly that spot, so you might have a valid file. Did you consider this, or is it prohibited because of the number of decisions?
No, I think that's actually possible, but it's sort of, if we consider sort of these specific corruptions, then we already need to take into account the file format itself, and we need to have more in-depth knowledge about the file format. So this is sort of orthogonal it's actually sort of goes against this black box approach, where you don't want to where you don't want it to be necessary to have this detailed information. What you can do in this case is that if you know that the file format is version 2, then you can just train it with files of version 2, and then it's likely, although not necessary, but it's likely that it will then have the same behavior for all files.
I understand that you explained that you measured the success rate.
Yeah.
But I imagine that the outcome of the reference tools and your outcome might also differ in quality.
Yes.
Did you measure the difference in quality?
Well, it's sort of difficult to measure the difference in quality. What I can say is that for the repaired images with our approach, most of them actually looked identical to the original. Some had some small artifacts. With the PIX recovery, the results were overall a bit worse. So what we did to compare our outputs with the originals for PNGs and JPEGs is we use this phash library, which is a library that produces sort of a visual hash. They have different metrics that compare the similarity of images, so they they are robust to some changes. For example, if you would change an image from color to black and white, it would still recognize it as the same image. So we used this, and we also did a visual inspection, and in the visual inspection, the results that our approach produced in general were of better quality than that of the reference tools, but of course this is not a objective metric because, yeah, well, it's a human output.
Thank you. Yeah.
You have ifs and else statements, but what would happen, and my programs have more loops than ifs and else statements. So what happens with loops?
So, I mean, this approach works on the binaries, and in the binaries we actually don't have loops. We have, and we don't have if and else statements. We have jumps, right? So, and there it doesn't really matter that much. So for loops we have usually 2 jumps. So one jump that basically goes back to the beginning, and then one jump to exit the loop. And since usually, or hopefully, if we have valid files, we will exit the loop at some point. At these jump statements, we will have both paths that can be taken. So for loops, in most cases, although not necessarily in all cases, this should actually not affect the behavior of the loop.
Yeah, so if I understand well, basically you want to shortcut any test that would lead to an error.
Yes, more or less.
Yeah, so I was wondering, why wouldn't you take the problem from the other side? So instead of looking at the tests, looking at the possible places where you see that you have error messages or things like this, and then go backward and see which test could lead to these messages. And in this way, you wouldn't have to train your system because you would have found all possible errors.
Yes, for that you first need to identify what an error looks like. So, and this depends on the file viewer. In a lot of the image viewers, an error doesn't really produce an error in the sense that that we actually get the output in some way that we can programmatically see the error, because we get a GUI that displays, hey, there was an error. So we don't get the error code as output because the program hasn't finished yet. So this is somewhat difficult to identify actually all of the points where you get an error. But there is actually an approach that is somewhat related to what we did, which is called do-covery, where they use symbolic execution to repair files, and that sort of goes in that direction, because you replace some parts of the file with symbols, and then basically want to solve for these symbols in a way that they don't produce an error. The drawback of that is that it takes a lot more time. So to repair one file, you need to do the whole symbolic execution, which is very computationally expensive. But it's also an approach that works surprisingly well. So these are sort of independent approaches, I'd say.
Any other questions? Maybe from this side of the room, or are you too busy enjoying the view? One more question.
You showed statistics and you grouped them by file type.
Sorry?
You
Yeah.
showed the statistics that were grouped by file type, and your approach is also always one flaw. Did you try to use different PNG viewing libraries that you have through your course often?
No, this is always regarding one program, because this is actually something that we found when we did the research. When I started out, I used ImageMagick as the file viewer, and then I generated a lot of corrupted files with ImageMagick, and it turned out a few weeks later that a lot of these files that ImageMagick wasn't able to open were easily opened with other file viewers. So we then switched to another file viewer that was more robust in order to not affect the get some false positives in the results. So this is actually regarding one file viewer where the files are corrupt with regards to the specification that is implicit to this file viewer. So the even though we have a PNG specification, not all PNG file viewers behave the same way when opening a PNG file. And so while they all open files that adhere to the specification, some may be more lenient and some less. And so a file that is corrupted with regards to one file viewer might not be corrupted with regards to another file viewer in the sense of invalid files. So that's why we concentrated on one file viewer. But in practice, I think you probably could increase the overall success rate even more if you use different libraries for these files.
All right, I think that's enough. Thank you very much, Karl.